a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the feather span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton feather span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Divided as to the cause of the disaster. Some claim it was the use of solid girders, others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
I have the regraded exam 1 here. If you want to be private, you come up here and get your regraded homework. Exam 1. Otherwise, you can pass them around. Okay? Is that okay? I put them here. And then you can come and pick them up after the class. We talked about resonance in the last lecture, and then we talked about resonance of an RLC circuit. Say if you have an inductor and then a capacitor, and then R, L, and C over here. You have voltage input over here, and then you can look at the current I. Okay, the current I over V, we can call the transfer function I omega over V of omega. And that actually is the admittance of the circuit. This is called the admittance of the circuit. And this is just equal to 1 over R plus J omega L plus 1 over J omega C. And then you can renormalize this equation so that it looks something like J omega RC minus omega square LC plus 1. Okay? So you can see that this is a RLC circuit that has resonance, but the resonance has been damped by this, yes?
So is this a ratio of current over voltage?
The transfer function, the response function can be defined to be a ratio of two quantities. Here I define it to be the ratio of the current over the voltage, and that is actually the reciprocal of the impedance. Okay, the reciprocal of the impedance is also called the admittance. Okay, and we define this to be admittance of the circuit. And it's just to show the fact that this admittance has resonances, and that if R equals to 0, then then if you look at this h omega, okay, then it will be equal to j omega c 1 minus omega squared LC. And when omega equals to 1 over square root of LC, which is that if you operate at resonance, what happens to the transfer function? The transfer function becomes infinitely long. And that is very dangerous. Okay? If you have a transfer function h of omega going to infinity, when omega equals omega naught, that is a very dangerous proposition. Okay? There's a dangerous proposition, and in engineering design, you try to avoid resonances as much as possible. And I'm going to show you this movie. I think many of you have seen this movie about Tacoma Bridge. And it's about designing a bridge that ignores resonance. What happens is that this bridge has its resonance modes. Okay? The resonance modes of the bridge seems to coincide with the periodicity of the gale or the wind that came by. In, I guess, Tacoma is somewhere in Washington, right? So there was a gale that came by every few seconds. And the wind that came by pumped the bridge and made the resonance bigger and bigger, and finally the bridge collapsed. It's very much like what you do in the park as you pump your swing. If you know how to pump your swing, you can get the swing to go bigger and bigger and bigger, and if some of you are dangerous enough, you can get the swing to go in a full circle, right? You never did that as a kid, did you? Okay? So let me show you this video. So there was a bridge designed by a poor engineer, and he did not know about the resonance mode of the bridge.
In a 40-mile-an-hour gale, the feathered fan waved like a ribbon in a swinging twist that you wouldn't believe possible, and legends could see it as you do now.
Oscillate bigger and bigger. Finally, the bridge was landed.
There's an automobile caught on the heaving roadway. The 11,000-ton feathered span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
Just like you pumping the swing.
Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Are divided as to the cause of the disaster. Some claim.
Okay, you can see this on YouTube. Okay, you can go back and Google Tacoma Bridge. Collapse. Okay, you can see this video on YouTube. Okay. Okay, are there any questions regarding this episode? So the lesson to be learned there is that when you design something, make sure that it does not have resonant modes, and they could be dangerous. Okay? And if the system does have resonant modes, you know how to attenuate the resonant mode. You can attenuate the resonant mode with this resistor. And if the resistor is non-zero, then there's actually no infinity here. And as you operate this system, it doesn't go to infinity, but if the resistor is equal to 0, then you get infinity out of this system. And that's no good. Okay? So, I'm going to start on chapter 6 then today and talk about periodic signals. Okay. Let's see what a periodic signal is. A periodic signal is a signal that has this property. Let me draw it first. Maybe it's more fun to draw it. And if I have a function of time, if it repeats itself every t period, that is called a periodic signal. Maybe the simplest one to draw is something like that. This is just one example of a periodic signal. Okay, you can draw other forms if you want to. It repeats itself every t period. Okay, even though my picture is not perfect, you can see what I mean. Okay, this picture repeats itself. Okay, and the periodic signal has this property that if you want to time shift it by t, it is equal to itself. Okay, everybody knows that this is time shifting, right? You want me to show you that this actually shifts the function. If you plot a function of t, okay, say if you plot this function as such, okay, this function f of t minus capital T would be something like, so when t equals 0, it's the same as ft equals minus t, so minus t might be here. Okay, so it's 0, and when t equals to capital T, it's the same as ft being 0. Okay, so this function will look something like this. So when t equals capital T, it's the same as when t is equal to 0 in the above diagram. So this function is just being shifted by a delay, capital letter T to the right. Okay, so everybody should know that. And a periodic signal has a property that if you were to shift it by a period t, it becomes itself again. Okay, but this is not periodic. This is aperiodic. This is periodic. Okay, and you can say something more general than that. In fact, you can shift it by an integer number of t. It becomes itself again, where n is an integer. Okay, that's a property of a periodic signal. And it turns out that if you have a periodic signal, you can have different ways of expanding the signal. Okay, that is called a Fourier series expansion. And it turns out that we have come across periodic signals before. For instance, this signal itself is periodic. And if you write in terms of cosine of omega t plus j sine of omega t, you can see that it repeats itself every capital T time interval. What is that capital T time interval that this function repeats itself? You can work that out. You say when omega t is equal to what, that this function becomes itself again. When omega t equals 2 pi. Okay, the smallest number is 2 pi. Okay, so omega capital T equals 2 pi. Okay, it repeats itself, but t is a period. T is called a period. Okay, in general, omega t equals to maybe omega tn equals to 2n pi, that would repeat itself too. But this is the smallest number that t can repeat itself, and then hence t is equal to 2 pi over omega. Okay, we know this from your undergraduate physics course, that omega is actually 2 pi times what? F, right? Omega is 2 pi times f. If you plug that in there, you get 2 pi ft equals to 2 pi, which means that f is 1 over t. So the frequency of your signal is proportional to 1 over its period. If you know the period of the signal, you know what the frequency is. And this is the smallest period that you can think of. You can create other kinds of periodic signal. Okay, you can create other kinds of periodic signals. And in the textbook, they use omega naught. Okay, let me just put omega naught here so that you have this symbol coinciding with your textbook. Okay, so maybe I can call this f naught too. So, but you can make other kinds of periodic signal. This signal is, if I were to plot just the real part, it will look something like this. It repeats itself every t period. Okay, this is time. This is cosine of omega t, or cosine of omega naught t. I can make other periodic signal by just multiplying the exponent by an integer. Okay, this is also a periodic signal. I can convince myself very easily. If this is a periodic signal, this is also the periodic signal, because if t equals to capital T, where capital T turns out to be 2 pi divided by omega naught, I get 2 pi divided by omega naught, and this is just e to the j 2n pi. Okay, and this is itself is 1 again. So you can see that this function, this other function, also repeats itself every t period. But if you were to plot the real part of this function, say if I plot it with 2 omega naught t, it will be cosine of 2 omega naught t plus j sine of 2 omega naught t. If I were to plot it on the same plot, it repeats itself much quicker than the previous plot. Okay, how often would it repeat itself? What is the period of this signal? If you were to think of it giving it a period as well. Yes? If the period of the top signal is capital T, what is the period of the bottom signal? T over 2, okay, it repeats itself over here. So it will just go like this, come down here and repeat itself, and then comes down again. I don't draw very well, so it repeats itself, and then come back again. Okay, this is cosine of omega naught t. This other one is cosine of 2 omega naught t. And you can draw the imaginary part as well. Okay, so the lesson to be learned here is that you can make periodic signals with higher frequencies by just multiplying the fundamental signal by n. Okay, so in general, you can make periodic signals in this manner. Okay, in this manner. These are all periodic. Okay, they're all periodic. The one with n larger than 1 also has a periodic property, but with the period being smaller. So what it says is that what Fourier Theorem says is that if this is periodic, I can write it as a superposition or sum of periodic signals with different frequencies. Okay, n equals to minus infinity to infinity. That's what Fourier series says. Okay, if ft minus capital T, where is equal to f of t, where this k is an integer. If the left-hand side is a periodic signal, then it can be expanded as sums of periodic signals, sum of different periodic signals. Every term on the right-hand side is a periodic signal, but with different frequencies. Okay, this is what Joseph Fourier said. I think he said it around maybe 1800s plus. Okay, around that period, he said that. Just shortly after the French Revolution. Okay, he made this statement. And this is a very powerful statement. Any functions of t that is periodic can be expanded as such. Okay? It's hard to prove it. It can be proven, but there are very systematic ways to find the coefficient f of n. Okay, you can find this coefficient f of n quite easily. And this is one form of the Fourier series expansion. You can also write the Fourier series expansion in other forms. Okay, this is called the exponential form. You can write it in terms of the trigonometric form. Okay, trigonometric form. And in that case, what you do is to actually write f of t being equal to the DC term, the n is equal to 0 term. When n is equal to 0, what happens to this function? When n is equal to 0, it becomes 1. Okay, it's a constant term. So I can say that I have a f0 plus n is equal to 1 to infinity, the positive n term, fn e to the j n omega naught t. Okay? And then I have the other summation that goes from minus infinity to n to 1. Okay? N is equal to minus infinity to n equals 1. Not 1, sorry, minus 1. Okay, the other half that I have not accounted for. And then f of n e to the j n omega naught t. Okay? I'm going to flip the sign of this n. Okay, I'm going to call n prime equals minus n. If I do as such, what happens to the second sum? So when n equals 1, what is n prime? When n equals minus 1, what is n prime? 1, okay? When n equals minus infinity, what is n prime? Positive infinity. So I can write the bottom sum as being equal to n prime equals 1 to infinity. F of n prime becomes minus n, or minus n becomes n prime. Okay? And then e to the minus j n prime omega naught t. Okay, but n prime is just a dummy variable. I could have called this n prime n without confusion. Okay? If I've called this n prime n, then I can combine this sum with that sum into one summation. So in the next line, let me write over here. In the next line, then I can say f of t would be equal to the constant term, which is also called a DC term because it doesn't change with time. Okay, plus the sum of this together with that. Okay, I can put them under one sum. N equals 1 to infinity fn e to the j n omega naught t, which is the first term coming from there. And then the second term is f of minus n e to the minus j n omega naught t. N is just a dummy variable. So I can call my n prime to be n again for the second sum. Okay? Then I can expand using the Euler's identity, expand this in terms of cosine and sine. What does Euler's identity say about this thing? I want to get the trigonometric representation. I want to find the trigo or trigonometric form of the Fourier series, which means that I would like to expand this in terms of sines and cosines. Some people love that better than exponential form. But in my opinion, exponential form is actually more elegant. Okay? But people are used to cosines and sines. So let's find the trigo form for that expression over there. So I will have to resort to Euler's identity. What is Euler's identity for this exponential form?
How is it minus?
What?
How is it minus?
What becomes minus?
Minus plus f negative n prime. When you find
I have this term, right?
yeah,
Sure.
Plus function two.
which changes the sign.
Oh, plus, yeah, plus, right. There's a plus sign over here. Thank you for pointing that out. If I use Euler's identity for that, I will have n omega naught t plus j sine of n omega naught t. Okay, for just this thing over here. And this will be just a complex conjugate of that. So if I were to rewrite this, okay, I can combine the cosines from the first term to the second term. Combining the cosines from the first term and the second term, I will get this times cosine of n omega naught t. Okay, I'm doing it kind of quickly. I can also expand this in terms of cosines and sine using the Euler's identity, but I get the plus sign for the cosine and the minus sign for the sine. And the second term would be something like fn minus f of minus n. Okay, sine of n omega naught t. Okay, so this is the trigonometric form. Am I jumping too fast by going from here to here? Or you can see it. Okay, you do in your head, this is cosine minus j sine of thing, and then you pick up the j and then you get the other terms. Okay, you get the other terms. So you want me to go a little bit more slowly. What is that?
Why did the n prime disappear?
Why does the n prime disappear?
Yeah.
N prime is a dummy variable. I could have called this sum without loss of accuracy as the same as minus.
Oh, never mind.
I could have called this sum by this name as well. If I call it by that name, I can combine with the first term without having to change my name. And then I can call the second term n, and I will have that. Okay? And then expand this one in terms of cosine of n omega naught t minus j sine of n omega naught t. Okay, that's the second term. I collect the cosines from the first term with the second term, I get this term. I collect the sines from the first term and the second term, I get the minus sign with the j there. Okay, I get this, what is known as the trigonometric form. And this is often written in a different manner. That this is called a0 over 2 plus n equals 1 to infinity. And this is usually called a sub n cosine of n omega naught t. Okay, and then the second term, this is often called b sub n. Okay, and this is often written as just b sub n sine of n omega naught t. Okay, and then the relationship between the trigonometric form and the exponential form is that a sub n is f of n plus f sub minus n, no 2, right? Just that. Okay, and then the b sub n is just equal to j f sub n minus f sub minus n. Okay, that is the relationship between the exponential form and the trigonometric form. If you know the exponential form, okay, you can rewrite the Fourier series in terms of trigonometric form very easily and get this thing. And what do you notice about these two terms? What do you notice about them? What is special about that two terms?
That's what
Yes?
that's what Euler did.
No? In terms of oddness. There's a joke. A horse has an odd number of legs. Isn't that odd? Okay. So which is odd and which is even? Cosine is odd? No, no. Cosine is even. Sine is odd. So by this trigonometric form, okay, you actually have decomposed the function, an arbitrary function of t, into two terms, the even term and the odd term. Okay? And it's the first term even or odd. even. Okay, if you were to pick out the even function of this, you have to take the first part. If you were to take the odd function of this, you will take the second part. Actually, there is a way to pick out the even part of a function and an odd part of a function very easily. The odd part of a function is equal to f of t minus f of minus t over 2. If you take a function and subtract the function with a negative argument, okay, and you can convince yourself that this new function has the property that f of odd of minus t, and if you were to substitute minus t in here, you get this to be f of odd of t. Can you see that? Okay. You can pick up the even part of a function very easily. It will be f of t plus f of minus t over 2. And you can convince yourself very easily that if I were to change this argument, change the sign, it just becomes itself. What this procedure says is that given any function that you have, it can always be broken into its odd form and an even form. Okay, odd here doesn't mean strange. Okay, you can break broken into an odd form and an even form, and that's how you pick out the odd and the even form. And if you have a Fourier series expansion in terms of trigonometric functions, the first part here is just f of odd. The second part here with the summation, okay, this part together with the summation is just f of even. Oops, sorry. What should that be? I make a mistake. Odd. Okay, of t. And this should be even of t. Okay? Let me draw a line. Is there any question regarding this?
Why use equilibrium models? Just sake of you.
Well, actually, what happens is that if you write it in terms of exponential form, then you will have to have a half there. The half would coincide with this half. Okay, I think that's correct.
No, because an equal to fn plus f minus n.
Okay,
So
you can also
plug in
think of it
n
that
equal to
way.
0.
So f of 0, okay, f of 0 is equal to f of 0 plus f of minus 0. If you were to use this formula, so this is like a0. So then you just put a0 over 2. I don't know what the reason is. Okay? But that is what is in the textbook, a0 over 2. You can put anything there. Okay? But it doesn't matter, it's just a DC term. Okay. There is a third form of the Fourier series expansion called a compact form. Compact form is just nice to write, because maybe it's shorter to write, but not very easy, I think. So in this form, what you do then is that you start with the exponential form, okay, omega 0 t, and then you write the f of n in terms of its amplitude, its magnitude times the phase. Okay, you write that in terms of amplitude times its phase. But if you know that the function is real, if this function is real value, you can actually say something about f of n Okay, if this function is real, okay, for every complex number you find in this series, it must be a complex conjugate somewhere. Okay, if this, let me repeat, if this function is real, for every function, for every number or every term in this series, you can find a complex conjugate term. Okay, so if f of t is real, if f of t is real, okay, if I take a term fn e to the j n omega naught t, what is the complex conjugate of this? It is equal to, the complex conjugation of this is fn complex conjugate e to the minus j n omega naught t. Okay? And if this term always has its complex conjugation as you sum this, okay? And this term must be coming from f of minus n. Okay? It says that if ft is real, f of minus n must be f of positive n complex conjugate. If this is the case, then for every term in this series, there is a complex conjugate, because f of minus n is just f of n conjugate. And when you sum this series, it always finds a partner. And the partner will cancel the imaginary part. Okay? So if f of t is real valued, okay, it implies that f of minus n is f of n complex conjugate. Is this clear? Or you need me to elaborate further on this in greater detail? It's okay, right? Larry, is it okay?
Yes.
Okay, good. So, if that is the case,